canonical representation of bandpass signal. So let S of t be bandpass signal, then pre-envelope of that bandpass signal is represented by equation 1. Pre-envelope is a complex expression where the imaginary portion is Hilbert transform of real part. And from our previous discussion, the complex envelope of the bandpass signal is given by product of this pre-envelope into the exponential signal. At the same time, complex envelope is given by sum of in-phase and quadrature component. What is quadrature component? It is Hilbert transform of the real part. So now we can define bandpass signal is nothing but the real part of positive pre-envelope. So this equation 2, which is showing the relation between the complex envelope and pre-envelope, can be rewritten like this. So pre-envelope is given by the product of complex envelope and exponential signal. Now substitute equation 6 in 5 and simplify. We'll get equation 7. What is the complex envelope? It is sum of that is in phase and quadrature component. Substitute this and get expression 8. Now equation 8 consists of imaginary term and real term. Let us reduce this expression and separate real and imaginary term. So after separating real and imaginary term, we are going to get equation 9. So simple mathematics, multiply all the terms and separate real and imaginary term as shown. So this expression, whatever shown in equation 9, represent the bandpass signal S of t in terms of in phase and quadrature phase component. And what is this cosine and sine represent? It is nothing but carrier signal. So now here this equation 9, which we considered as standard form of canonical expression for bandpass signal. So here we can write phase diagram for in phase and quadrature phase component and rotation of this exponential signal. So when you multiply this quadrature component with exponential signal, we're going to get projection of the bandpass signal on real axis. So there are two parts in analyzing equation 9. Given in phase and quadrature component, you can construct bandpass signal. Part 2, given S of t, that is bandpass signal, you can extract quadrature component. So from equation 9, we can able to write the block diagram here. So write Si of t, Sq of t, generate a carrier cos 2 pi fct, multiply that with Si of t, and you will get the first expression. Now pass that cosine signal through 90-degree phase shifter, multiply it with quadrature component, you will get Sq of t sin 2 pi fct. Here we have summer, so you will going to get the expression S of t. In a similar way, if in phase and quadrature components are given, you can able to get the S of t. In a similar way, we can extract in phase and quadrature component from S of t. So use equation 9, multiply both sides of equation 9 by 2 cos 2 pi fct and simplify using trigonometric equation as shown here, and equation 10 reduces to 11. That means S of t 2 cos 2 pi f c t is equal to in phase component plus higher frequency component. So when I pass this signal S of t 2 cos 2 pi f c t through a ideal low pass filter, it eliminates the high frequency component, producing in phase component. In a similar way, if you multiply equation 9 by minus 2 sin 2 pi f c t and simplify, you will get the quadrature component that is represented by equation 12. When you pass S of t minus 2 sin 2 pi f c t through low pass filter, it eliminates high frequency component, producing only quadrature component. So write the block diagram. Given band pass signal, multiply that by carrier signal, that is 2 cos 2 pi f c t, and pass that through low pass filter to produce in phase component. So pass this carrier through 90-degree phase shifter, multiply it with S of t, pass it through low pass filter in order to get quadrature component. So this completes module 1 part 1. In this part 1, we studied Hilbert transform, definition of Hilbert transform, proof of Hilbert transform properties, and then some problem we solved, followed by the concept of pre-envelope and the complex envelope. We solved some problems on complex envelope, and then we analyze the canonical representation of bandpass signal.